Hey, APChem gang. I want to give you a heads up as you're looking through these annotations and kind of explain something because there's a few of them that get kind of busy. But you guys are doing good. And there's a few key things that you need to remember when you're dealing with these acid bases. And a lot of the problems come down to understanding what this is, that way that we go about solving acid-base problems. And the first thing is, and it happens in a lot of the problems here, you have to have a balanced net ionic equation and know what that net ionic equation is that you're dealing with. Second, you need to know when you're using stoichiometry or an ice table, like a BCA table or an ice table. BCA table, if you have a strong acid or base, regardless. And if you have one of them, if you have two of them, that's or if you have like a strong acid and a strong base, or a strong acid and a weak base, strong base and a weak acid, doesn't matter. If there's something strong, you have to do a BCA table, most likely. And then if you are dealing with a weak acid or base, you will have to do an ice table, but it kind of goes in this order. Write out your net ionic equation. If you have a strong substance, you have to do the stoichiometry. And if you have the weak substance in there too, you have to do the ice table next. And so it kind of goes in this order. But then there are shortcuts. And the biggest shortcut is going to be this Henderson-Hasselbalch. And because the Henderson-Hasselbalch, you can skip over this ice table. And I'll show you that. And so hold tight. And I'll kind of point out a few problems on here. And some of them, like I said, get busy. So there are some things here where I show a lot of work, but in many cases, you don't have to show the work. You can actually reason through it and be able to get an answer without necessarily showing all this work. And like you could maybe skip this BCA table because you know that this completely dissociates, and you can just say what the concentration of H plus will be of this substance. It's the same as the concentration of that acid, and because it's a strong acid and you're only dealing with one. But I showed that information just to kind of back up some of the stuff that we had talked about. And yeah, that's kind of the gist of it. But the ones that get busy are things like number 13. Oh boy, number 13. And then number 14 and number 15. And I'll come back to those here in just a second. But then when we kind of get down here, number 18 I'll talk about here really quick. And then it starts to get busy again here, I believe, around number 27. Yeah, number 27, 29, and yeah, that should be kind of where it's at. So I'm going to go back up here to number 15 first. That's the first one we're going to talk about, because this one gave you a pKa, and it was a combination of this NH3 and this HCl. So they asked you, based on the pKa and the data given in the table, which of the following gives the pH of the buffer solution? So in here, you go through those steps. One, you need the net ionic equation. You're mixing together this NH3 and the HCl, which dissociates completely into H plus and Cl minus. So the Cl is going to be a spectator ion. You can leave it out. So for strong acids, you can leave out the anion. But then we just have NH3 plus H plus yields back and forth between NH4 plus. That's really all that you need. And because that's what this equation is saying. But they give you molarities, and they say the concentration of both is cut by 1/2. So these are really the molarities that you're dealing with. And here they also do not tell you a volume, like how much of those things that you have. And here it really doesn't matter. you can kind of make it easy on yourself and assume easy volume. Just say it's 1 liter of each because they say it's equal volumes. And so you can just choose, and that's fine. You can do that. But because we are dealing with a strong acid, and our next step has to be the BCA table. And so we set up our BCA and we put in our initial number of moles. It has to be moles. So that's what was figured out down here from the molarity equation. It gave you the molarity. We're assuming a volume of 1 liter. Great. Figure out the moles. We set up our change, minus x plus x. Oh, sorry, we had 0 here for the starting. I didn't list that, but it's 0. Then you get your after pieces, and because this is our limiting reactant, we have 0.06 moles here, 0.05 moles here. It's our limiting. It becomes 0. We don't have any left at the end, and then we can solve for that x, and then solve for how many moles that we have for each. So we have that. Now, you could go ahead and actually do the next step, which is going to do an ice table, because you are dealing with a weak base and a weak acid. But because you have conjugates, you have the conjugate base and the conjugate acid. These are the conjugate pairs. You have a buffer solution. They even tell you got a buffer solution. And so because we have a buffer solution, there is a shortcut. You can skip the ice table and you do Henderson-Hasselbalch. That is what we want to recognize, and that's what we want to do. And in that Henderson-Hasselbalch equation, you could use moles. And so Henderson-Hasselbalch, pH equals pKa plus the log of A minus over AHA. Nice, they gave you the pKa for this substance. That's the one that you use. It's the 9.25, and plus the log of A minus. That's the conjugate base, the NH3. So you have 0.01 moles on top, and you have 0.05 for the conjugate acid on the bottom. And if you do the math, it comes out to be 8.55. And that matches up exactly with this. So I'll show you an example here in just a little bit where if you do the ice table, you can get the same answer. It's just a whole heck of a lot longer process. But if you recognize that you have a buffer, and after doing the BCA table, all you have is the conjugate pair, and then you can do Henderson-Hasselbalch. And so that's kind of nice. It's a shortcut. But let's take a look at the one that is written out really long, and that's number 13. Oh boy. And so they gave you a pKa, and they told you you're mixing together CH3COOH and the NaOH, and this is kind of how it was written out. Start off with your net ionic equation. Here's your net ionic equation. CH3COOH plus OH minus, that comes from the NaOH. The Na will be a spectator ion because it's a strong base. Yields, and that should be back and forth, CH3CO minus plus H2O. We don't have to worry about H2O, so we kind of cross that part out. So that's step 1. Step 2, we have to determine if we have to do a BCA table, and yes, we do have to do a BCA table because we involve a strong base. And so that's the NaOH, and that's where this OH minus is coming from. We need to put in the original amounts, but it has to be in moles, which that's this part here in the green that's worked out. It takes the molarity of the NaOH and, of the CH3COOH, and it converts it to moles of CH3COOH. That's where we plug it into the before number of moles in the BCA table. We start off with 0.0200 moles of OH minus. We assume we don't have any of the CH3COO minus. We put in our change, but because this is our limiting reactant, we have more of this substance than this one, and it's a 1-to-1 ratio. That means that if this one's going to end up at 0, we can solve for what that x is. It's 0.02. And then when we can solve for our substances here. And now, because what we're left with is just like what we had before, we can actually take that shortcut and do the Henderson-Hasselbalch equation. You can put moles in it. It doesn't have to be molarity. And we can skip the ice equation. If we do that, we end up with exactly like this equation here. pH equals 4.76. That's the pKa, plus the log of A minus, that's the conjugate base part, and this is our conjugate base, 0.0200, divided by our moles of our HA, or our conjugate acid, 0.0550. And then if you solve it out, you get 4.32. And that's the easy way of doing it. But you have some work that you have to show to get it. And then, there are shortcuts too. We're not gonna worry so much about that. And if you know what the shortcuts are, great. But even if you didn't recognize to do the Henderson-Hasselbalch, you could do the ice table. You rewrite the equation, but it has to be a molarity. So it has to be moles over liters. You have 500 liters in the solution because this one was 500 milliliters. And then you take the moles divided by liters, moles divided by liters for this one. That's going to give you your concentrations. You have 0 for the OH minus because from here it was your limiting and you don't have any. Then you do your change part, plus x minus x. And because it's going to shift over to the left side because you don't have any OH. And you end up with these for the equilibrium values. But you can, when you go to use that equilibrium values, they give you pKa, but this is a Kb expression because it has OH minus. So you got to convert it to a Kb expression. You can relate pKa and pKb to each other because they add up to 14. You solve for the pKb, figure out what the value for Kb is. It's 10 to the negative K. Sorry, I should say negative Kb. And but your expression needs to have the OH on the top. So it's this stuff is on top. This is on the bottom. It's kind of backwards. So yeah, don't worry so much about that because this is a long problem. And but anywho, when you work it out, you can assume that the x's are not significant because this value is much less than negative or times 10 to the negative fourth. And then, hoofta, you can go through and solve for OH, solve for the POH, relate it to pH, and you get 4.32. It's the exact same thing that you got here. Oh my gosh, that is a lot of work. But if you took Henderson-Hasselbalch, because you had conjugate pairs and that was it, you're good. And so that's number 13. Number 14, you have strong acid, strong base. Oh man, just a BCA table. There's no ice table involved here. So this is going to be easy. You just have, and your net ionic equation for a strong acid, strong base, the Cl, that's going to be a spectator ion. Na, that's a spectator ion because they come from strong acid, strong bases. They're not going to connect with anything else. So you have H plus OH minus yields H2O. Forget about the H2O. And you put in moles, got to figure that out, and then set up your minus x plus x. This is your limiting reactant. You have OH minus left over, and now you can use that OH minus concentration to figure out POH, and then to figure out your concentration of it related to pH. You get pH equals 12.68. And that's kind of what's going on there. And so, yeah, this thing. But those are those problems. I'll kind of put in a separate video these last few from 18 on, and then we should be good. You guys are doing an awesome job. Thanks for following along with this, and let me know if this is helpful. Okay? But we'll talk to you later.